So that explosion was your finale to gas laws, and now we're going into thermochemistry. Okay, so thermochemistry. What does the word thermo tell you? Heat. I know you guys are going to say heat. All right, yes, kind of ish. Okay, so it has to do with, we're going to be analyzing temperatures. We're going to be analyzing energy, all right? So it's a transfer of energy, and we're going to watch how certain reactions give off energy or need energy. We're going to be breaking bonds and forming bonds and all this stuff, okay? And the vocab is going to be very, very, very important on this one, okay? So I kind of cringed when you guys said heat. So let's talk about the word cold. What is cold? Is cold like actually a thing? Because I don't think it is. What is cold? Like when it's not hot, yeah. What is hot? All right, so I like that she's relating it to kinetic energy, but let's just not even use the word cold because cold doesn't really exist. Cold is like a thing that we made up. So it's a lack of kinetic energy, all right? So it's a lack of your molecules moving, okay? So you really want to think like a chemist and get down to that molecular level whenever you're thinking about these words, okay? I don't want you to use regular old language that you've used every day because heat is also not something. Because last period they said, oh, well, it's a lack of, you don't have enough heat in you. No, because technically heat is energy moving. So like moving from one thing to another. So we can't say that you're full of energy moving from one thing to another within you and like what, right? So you really want to be specific about a lot of your words. We're going to be really specific about what a system is and what its surroundings are. Okay, so you in your desk, like you know that you could be little system. And the room that you're in right now is your surroundings, right? Or we could say the room is the system, and then the hallway out there was our surroundings, right? So we are going to get to change all of these things, all right? And so I just want you to know how much control you have in this, all right? All right, so to start us off, I also want to make a side note that I'm only going to get you guys as far as you need for your benchmark, and then we're going to take our benchmark, and then we'll finish thermo after, okay? So we're going to go right into calculations, and I apologize because that's not how I like to start this unit, but we do need to learn the calculations first, okay? All right, so the first thing that we got to talk about is our new unit. So we have an SI unit of energy, and that's called the, does anybody know? Joule, good. Okay, joule. And heat and work are also measured in joules. So let's go ahead and put what our variables for heat and work are. And that's going to be a Q and a W. And together, those things are going to make internal energy. Okay? So we're gonna be analyzing a lot of stuff with energy. Okay? But I want you to notice this is that thing that I was talking about with heat. It's energy in transit. It's energy between things. Okay? So something doesn't contain heat. It contains energy. All right? Okay. The next word on this page is going to be a calorie. This is not the same as your food calorie. This one is actually, your food calorie is actually a kilocalorie, kcal, okay? And it's just a little different, but it's the same, it's kind of the same idea. It's the fact that it needs to absorb energy in order to change temperature. So when we think about burning calories, it's kind of where it's coming from, all right? So, but I just want you to know this is not the same calorie that you read on a food label. Not the same. This one is specific to water, okay? And on your formula chart, you guys have calorie on it. Look on the inside real quick. You have 1 calorie in there. You have this number right here. So make sure you look for it. Okay? Okay, so you have 4.184. You see that? This number is going to be used in a lot of your calculations when we're analyzing water, all right? So your first lab that you're going to do is talking about how water is either going to absorb energy or it's going to lose energy to this other item. And so this 4.184 is going to be important. Now, I want you to think back to this little definition, okay? When else have we heard about absorbing energy in order to get hotter or whatever, warm up? Well, endo with exo, not quite. Do you guys remember when we talked about water? A lot of you guys put it in your essay. You talked about how the oceans. No. Is this? You guys remember using the word heat capacity in your, some of y'all did. Oh, you knew it? Okay. All right. So some of you guys like threw it in there and I was like, oh yeah, I'm sure you know. All right. So heat capacity. Now we're going to actually be using that, okay? And so a calorie and heat capacity are going to be the same thing, except that specific heat capacities are going to be used in your calculations because you can use them for a lot of different objects, okay? I did not mean to cross that out. You do not need to cross that out. I'm so sorry. That's why I rewrote the C. Okay? And whether or not you put the P, I don't care. That's what I'm used to when I taught physics. You can or you don't have to. Be ready for both of them. But I wanted you guys to know that the calorie and that are the same thing. That's why this number says calorie, okay? But this is the specific heat of water. This is what you can use, okay? All right, so it depends on how big your sample is, and it depends on chemical composition. So I want you to think back again to what I was just talking about. What was the thing that we talked about in the middle of summer that shows two very different heat capacities? What is something that you guys go to in the summer? A pool, right? So in the pool analogy, we talked about how the water feels like what? Did the water feel like it was boiling in the middle of a summer day, or did it feel pretty cool? Pretty cool, right? Okay, so this one had a high specific heat. Okay, and therefore it felt cooler. It takes longer for it to boil, if you will. All right. What was the other part though that has a very low specific heat? Which part burns? The concrete. Thank you. Yeah, concrete and metal. If you've ever like gone to a car, has anybody gotten burned by their seatbelt?
Yes.
Oh, it's the worst. All right. Okay, or even at the pool, some of those chairs with the little metal, oh man, yeah, it's horrible. All right, so those things have low specific heat. Those things, it only takes a minuscule amount of energy for it to increase temperature. So if you imagine it's been out there absorbing tons of energy, obviously it's going to be raising tons of temperature degrees, okay? So, just remember this when you are trying to decide if something has high CP or low CP. I want you to think about the pool, okay? All right. This is kind of a little recap of what we just talked about. This is about your units. We'll get back to that when we start calculating. Do you guys have any questions over any of this? Okay, so, and even more, just so we're aware, this is good for life, helps maintain homeostasis, the idea why water is really important to all of us, okay? Okay, so the formula, this is the math part that I said we're going to start, okay? So your formula is going to be Q equals M cat. And I am so sorry we have another cat equation. I'm really starting to sound like a cat lady. My nightmare. All right. So, anyway, Q is heat, C is your specific heat, M was the mass, and delta T is your change in temperature, okay? Please note, this little delta is not an A. We just say MCAT because it looks like it if you look at it, okay? So please don't be looking for the A. A lot of my students last year, I shouldn't be calling them out on video, sorry, but they sat there and they were looking for the A and they were like, where's the A, Miss Fogel? What is A? And it took me forever to realize what they were talking about. That is not an A, that is a delta symbol. So let's talk about what that means. Change in temperature, right? But what does that mean? So it's temperature. We have to have two different temperatures. What do you think those two different temperatures are going to be? Final and initial. So which one goes first? I mean, good. We do temperature final minus temperature initial. So you guys remember in math class when you guys did slope? Did you notice that you did y2 minus y1 and x2 minus x1? It's the same idea. Okay, that's how you figure out your change, whether it was a positive change or whether it was a negative change. You see where you ended up. Okay, we start there. All right, red is obviously not the color to use, so I'm going to change back to purple. Okay, so we're going to be using this, and we are going to use it specifically in a lab that hopefully we do on Tuesday. Okay, and it's called Calorimetry. Okay, I'm going to write it up here. Calorimetry. Okay, calorimetry is just going to be the measure of heat flow into or out of a system. Now, there's that word system that I told you about. Okay, into a system, you're going to have a positive flow. Out of a system, you're going to have a negative flow. So this is kind of an intro into directional numbers for you guys. Okay, and that, especially my people moving on to physics, that's going to be important to you, especially at the beginning of the year. Okay, actually it's going to be important the whole year. Positives and negatives mean direction. So for us, going into our system is going to be positive heat flow, and out of our system will be a negative heat flow. Okay, so it's based on the fact that heat released equals heat absorbed. So another way to write that is heat released minus Q is equal to positive Q. And you can replace both of those Q's with that formula that we just learned. Okay? So you can have MCAT equals MCAT. And you should be getting the same thing. We're not creating or destroying any energy, right? Conservation of energy. All right. So when you guys go to do the lab, you're going to be using this thing called I keep doing that, calorimeter. Or some of my kids last year called it a calorie meter. I don't recommend you saying that anywhere but this classroom. Okay. So you're going to use a calorimeter, and it's a really expensive device. It's coffee cups, so make sure you don't break them. Don't squeeze them too hard. I'm just kidding. All right, they're the styrofoam little coffee cups that you can buy like for a cent. All right, so we are going to be using those. What we're going to do is we're going to stack two of them. You can kind of see it in this picture if you look closely. They have different stacked cups, and then we actually are going to put it into a beaker to kind of get a little extra air insulation in there as well. And then we got to put a lid on it. Why do you think it's important for us to put a lid on it? To trap it, right? To keep it a closed system. So now whatever is inside the cup is our system, okay? And we don't even worry about these surroundings, right? So actually more specifically, I'm sorry, whatever reaction is in your cup is the system, and then whatever is surrounding it, so usually it's water, is your surroundings. And now you're able to actually capture everything in system surroundings kind of thing. It's contained, okay? Yeah, so it'll be really cool when you guys see it. It's kind of a boring lab, I won't lie to you. And if you're going to regular physics, you're going to do it again next year. Sorry. So, but you might as well learn it this year, so it's easy next year. But what you guys are going to do is we're going to heat up metal, and we're going to put it into water. And you're going to measure the water, because technically whatever that metal loses, the water should gain, right? Okay, so that's calorimetry right there. That's heat flow. So that's what we're going to be analyzing, okay? Now, go ahead and flip the page. Oops, that wasn't what I meant to. To specific heat calculations. So don't worry about the vocab yet. Just go to the calculation side. Okay. So for your specific heat calculations, let's go ahead and write at least our formula so that we're ready to work on these when we come back on Monday. So the one that we just got was Q equals MC delta T. MCAT. Okay? All right. So we're going to expand this a little bit, and we're going to make it, I want to see if this one shows up. Yes?
Yes.
Oh, ugly Q. We're going to expand this to just say temperature final minus temperature initial. Oh, that's a good color. Why wasn't I using that one? Man. Okay. So what this sets you up for is I can give you all the other information and ask you what is your thermometer going to read, right? So I can give you all this stuff, and you can solve for things like temperature initial and temperature final, okay? This first question is actually asking you to solve for your C. So write this underneath that one. Sorry. C. So how are we going to solve for C? We leave C there, move everything else. Who's on top? Q is on top. Yeah, TF minus TI. Yep. Good. Okay. And so those are kind of three versions of it. When you run through your problem, I'm just going to run you through a little bit of this first problem, and then I promise we'll pack up. So when 34,700 joules of heat, all right, so heat, what variable do we use for heat? Q. So we're going to say Q is equal to 34,700 joules. Okay, are applied to. All right, so let's actually listen to what that word is saying. If it's applied to, is that a positive heat or is that a negative heat? Plus, because it's going into, right? So we're going to put a little positive above it so that we know that it's going to be a positive number. All right, to a 350 gram sample. So M is 350 grams of an unknown material, and the temperature rises from, and now we have our temperature change right there. So delta T is going to be T final minus initial. So 173 was our final. Our initial is 22. So we get 151 degrees Celsius. The cool thing about thermo, we don't have to convert that to Kelvin anymore. It's not necessary. Gas law is absolutely necessary. For thermochemistry and thermodynamics, not always necessary. You can, but you don't have to. Okay, so we're going to leave it Celsius. And now they want us to solve for specific heat. So we're going to say C is equal to, and we're going to use this guy right there. It's just a straight plug-in. Okay, so I would say the most difficult thing in this unit is making sure you put things with the right variables. And that's all I've got for you. Do you guys have any questions?
No.
No? Okay. All right.